In this video, we're going to be looking at the graphs of power functions, and then in future videos comparing them to the graphs of exponential and log functions. I want you to take a minute, maybe pause the video, and look at these four graphs and see how they are similar and how they are different in the shape of the graphs and in the equations and the points they go through, etc. Okay, you may have noticed that all four of the graphs, both the three over here and the one over here, have an equation that looks very similar. The equation is in the form f of x equals ax to the b, where the variable is the base. The only one that doesn't seem to have a b here is the 2x, but we could think of this as 2x to the first. If that exponent b is a 1, this is really a linear equation, so we don't really count this as a power equation, but it has the same form as a power equation. This is known as a power function. It is something variable raised to a power. Now, how are the shapes of the graph different? What I want you to notice is when the power is greater than 1, this grows faster than the linear graph. Initially it kind of starts out slower, but it eventually crosses it and grows faster. So when the shape of the graph depends on the exponent. So when the exponent, and that's b, when it's greater than 1, we have a shape that looks like this. Now we can see we have here where the exponent is positive but less than 1. So we're going to say when the exponent is between 0 and 1, then we have a shape that looks like this. Now notice both of these go through the point 0, 0, because when in this equation, if x is 0, we have 2 times 0 to the 2.4, 2 times 0 to the 0.3. So both of those are equal to 0. The third one, though, when the exponent is less than 0, when we have a negative exponent here, this has a completely different shape. It has two asymptotes that it runs along. So both the x and the y-axis are asymptotes. Notice that it is undefined for x equals 0 because this is the same as saying 2 over x to the 1.5. This is undefined at x equals 0, so it has no y-intercept. So these are the three characteristic shapes of power functions. And these actually should look kind of familiar to you because some of our parent functions have those shapes. So if we look at our parent functions here, we can see that these all six of these parent functions can be written in the form f of x equals a times x to the b. In every one of these, a is equal to 1. So 1 over x can be written as 1 times x to the negative 1. This can be written as 1 times x to the 1/2 power. This is 1 times x squared. This is 1 times x to the negative 2. This is 1 times x to the 1/3. And this is 1 times x cubed. So notice, if we look at the characteristics here, in a and d have exponents that are less than 0. So they both have this shape in quadrant 1. Now hopefully you remember that 1 over x also has this part down here in quadrant 3, and 1 over x squared has this part in quadrant 2. The middle two have exponents that are between 0 and 1, so notice they both have this characteristic shape in quadrant 1. The square root of x is undefined for negative x values, but the cube root function then continues on like this. So if we're looking at their characteristic shapes, we're seeing this characteristic shape in quadrant 1 that we saw above. The last group has exponents greater than 1, so they have the upward shape like this. Now I'm going to give you a word to help describe this. Of course, and this is an even graph, and then this is an odd. That's very pitifully drawn. Let me try that again. needs to look very symmetric. And this is an odd graph. So these two graphs have this upward shape. Now, how do we distinguish between this kind of a downward curve and the upward curve? They're both increasing, they're both growing. We call this one concave up, like a cup. We call this one concave down, like a frown. Okay, so it's curving down, it's concave down. If it's curving up, it's concave up. Now, notice that when I talked about power functions, I only am looking at all these four graphs in the first quadrant where x is greater than or equal to 0. Why are we only looking at quadrant 1? Well, I want to show you this on Desmos. Okay, so right now we have a is 1, so our coefficient is 1, and right now b is 1, so this is linear. If I make b bigger than 1, we see this characteristic curve forming in quadrant 1, this concave up curve. And if I make b between 0 and 1, we see this concave down curve. And if I make b less than 1, we see this downward slope. But what I want you to notice is what's happening on the other side of the y-axis as I move. Sometimes we have an even graph. Sometimes we have an odd graph. Sometimes there's nothing at all on the other side. It just depends on what b is. And that's because when I have non-integer values of b, I'm actually using rational exponents. So 1.5, for example, is 3/2, which means it's something to the square root of something to the third power. Well, we know that square roots are undefined. So when we have exponents that are non-integer exponents, decimal exponents, we're actually doing roots, and some roots are undefined for negative numbers and some are defined. And so we have all kinds of different things happening on the other side of the y-axis. So the only thing that we can be sure of being constant all the time is its shape in quadrant 1. So to summarize, if x is less than 0, depending on b, the function is sometimes undefined. Sometimes even, sometimes odd. So we just look at quadrant 1. And you're going to find out that when we're talking about power functions, we're usually talking about using them as mathematical models for something, and that's usually more appropriate for x greater than 0 anyway.